It's my pleasure to welcome you to the second lecture in this distinguished faculty lecture series. Thank you for coming to celebrate the accomplishments of our faculty. My name is Royce Engstrom. I'm the provost here at the University of Montana. Been here for a little over 2 years and loving every minute of it. It's been really gratifying to restart this lecture series as one way of recognizing our university's most outstanding faculty members, our greatest asset, our faculty. Those of us who have finished our formal higher education have fond memories of faculty members along the way who were especially effective with us, especially influential. It might be someone who presented brilliant lectures, who clarified challenging questions or complex topics. It might have been a mentor who took a personal interest in us, brought us into their research laboratory or program. It might be an accomplished scholar who served as a role model and really excited us about a discipline that we hardly knew existed at the time. For those of you who are currently students, I hope that you've found such a faculty member that has been influential to you, and if you haven't, I hope that you do before too long. These are folks to be cherished, and I can tell you that you will remember them throughout your life, and they will be influential to you long after you've left their classroom. To this day, I remain inspired by several faculty members who seem to take as much time as I needed. They seem to spend more time in the class and in their material than I did. They cared deeply about their students, and they cared deeply about the ideas they placed in front of us. It, again, is a true treasure to have a faculty member who played that kind of a role. The duties of a faculty member here at the University of Montana, and in fact at most universities, are typically expressed in a tripartite assignment: teaching, research or scholarship, and service. It's expected here at the University of Montana that all faculty members engage enthusiastically and productively in all of those areas. The faculty members that we're recognizing in this lecture series have been themselves recognized by some outside group for their outstanding work in one or more of those three areas. We began the series a few weeks ago this fall with Professor Jackie Moore from the School of Business. She is our university's most recently designated Regents Professor. Tonight's lecturer will be introduced in just a few minutes, and you'll see why he was selected. And we'll have our third and final lecture of the series on November 10th, presented by Professor Scott Mills from the College of Forestry and Conservation. He was selected as a 2009 John Simon Guggenheim Fellow. We're so proud of these three faculty members, and we're proud of the University of Montana faculty as a whole. Before we get started, I want to recognize the work of our sign language interpreter, Denise May. And Denise, thank you for your work. Let's give her a hand for the hard work that she did. I would also like to remind you that we'll have a reception after the lecture, and so if you don't get your questions answered with Dr. Smith during the question and answer period, be sure and do that after the lecture, but we hope all of you will stay and join us for conversation. Well, I'm pleased at this time to call upon our Dean of our College of Arts and Sciences, Dr. Chris Comer, to introduce tonight's speaker. Dean Comer is in his second academic year with us, and he's off to a great start as the leader of our largest college. I'll leave the details of the introduction to Dean Comer, but I can't resist saying that tonight's speaker, Garon Smith, is a fellow chemist. I knew him before I came to the University of Montana, and I knew of him long before that. I think most of you know he has quite a reputation, not just here at the university, but around the country as a flamboyant and effective teacher. I'm sure he's going to live up to that tonight. The other thing about Dr. Smith is that he doesn't follow directions from the provost very well. And I'll let him tell you more about that. At this point, would you please welcome Dean Chris Comer.
Thanks, Provost Engstrom. If you've ever had the chance to sit and talk with Jim Foley, who's the Executive Vice President here on campus, he likes to think a lot about marketing and public relations, and he will tell you very quickly that the most recognizable symbol in the state of Montana is Main Hall here on this campus. It's instantly recognizable just from sight. I have a strong suspicion that tonight's speaker is the second most recognizable emblem in the state of Montana, Professor Garon Smith. Garon is an environmental and analytical chemist, and he's got an interesting hybrid background. He studied environmental biology at the University of Colorado at Boulder. He then studied applied chemistry at the Colorado School of Mines, and after teaching at other institutions, he came here in 1991. One of the things I really admire about Garon is that he's one of those classic faculty we have who teaches across the curriculum. He teaches introductory level chemistry to large groups of students. He teaches upper level courses for undergraduates, and he teaches specialized graduate seminars for graduate students. And this is exactly the way teaching happens at its best. His teaching has been so highly recognized, you may remember that he was named in 2008 the Montana Professor of the Year by the Carnegie Foundation. And if you look at his vita, he's won numerous teaching awards, and they've included things like for faculty service, and the one I like the best, most inspirational teacher. That's not something that would come lightly from the students. Garon, as you may know, has an alter ego, which you'll see tonight. He travels around in the person of Garon the Wizard or G-Wizard. And he makes, in this role, somewhat upwards of 50 appearances each year at schools around Montana. And that, I think, indicates a real dedication to engagement with the public in the issues of science. Dr. Smith is a senior associate with the National Center for Civic Engagement, the Sensor Project. His civic engagement is also indicated by lots of other interesting activities he has, and I don't know how he has time for all of these. He's chair of the local Board of Health, the Air Pollution Control Board, the Water Quality District Board, and for 10 years he's been the governor's appointed scientist on the Montana Board of Environmental Review. At the level of national civic engagement, something that I think you should know, he has worked with the National Conference for Undergraduate Research, and in 2000 organized a conference on undergraduate research. He's doing it again this coming year, 2010, and I'm happy to say this will be on our campus, and it's going to be April 15th to 17th. That's going to be very exciting happening on campus. We're all getting geared up for it already. Last but not least, what does Garon think about? I can't tell you, but you're going to get an insight into something about what's going on in his mind tonight. I know he has thought about interesting topics like how honeybees can be used to detect landmines, how to make biodiesel and lubricants from vegetable oil, how do you follow the dispersion of pulp mill odors as they flow through the mountain valleys of Montana. And what you'll find out tonight is he's also given some great thought to snowflakes and color and other fun stuff. It gives me great pleasure tonight to introduce Professor Garon Smith.
Thank you, Dean Comer and Provost Engstrom. I figured people would probably expect me to come here in my wizard outfit and do a bunch of wizardry tonight. And so I thought I probably would do a couple of things just to make sure that I didn't disappoint anyone. But when Provost Engstrom says that I don't follow instructions very well, he asked me to give a talk to the incoming freshmen over in the University Theater, and he said, I don't think this is a very good venue for you to do any of your flaming tricks. And I wasn't sure I agreed with that. So I got up in front of all of the students and said, do you think I should follow my new provost's instructions? I said, I think I could be much more exciting if I disobeyed him. Do you think I should disobey him? And I like to please the students, and they said I should disobey him. So I tore off my academic robes, and underneath I had my wizard costume. A couple of people mentioned that it looked like I'd gained a little bit of weight over the summer. Well, it was my wizardly robes. And I thought I would use my standard opening trick here just to demonstrate the kind of wizardry I like to perform to school audiences. I love doing that. If you ever wanted to feel like a superhero, dress up in a wizard suit and do chemistry for second graders. And you really are a wizard to them, and it's just terribly massaging to your ego. So I try to convince them that when I go over to Hogwarts and substitute for the potions teacher, in second-year potions, I teach them how to do the ink spell, which requires you to use a couple of potions. And if you've formulated them correctly, you can mix them together, pronounce a spell, and turn them into ink with your magic powers. The spell goes, when east is east, and west is west, and one flies over the cuckoo's nest. When red is red and pink is pink, make this water black as ink. And then you rub with your magic fingers real hard. And it's supposed to turn into ink. Uh-oh. Rub again. Why isn't this working? I've never had that fail before. Uh-oh. Magic fingers are gone. I don't know why it didn't work. Let me try the, maybe it was the container. Like I say, this is new. You never know what's going to happen. Maybe I didn't wash out the big flask and it had some residue. We'll try it in the smaller ones. Let's see. I don't think I left out any of the ingredients. It's not making a good impression on my new dean. We'll try this again. Pour them together. Say the spell. When east is east, and west is west, and one flies over the cuckoo's nest. When red is red and pink is pink, make this water black as ink. And then I rub it real hard. Maybe I have faulty solutions tonight. I'm going to have to check that one out. Like say, I've never had that one fail on me before. Oh, well. I thought what I would do this time is the reverse of what I did with Provost Engstrom. I'd start out in my wizard gear and then get more respectable. So we'll get rid of this, particularly since it doesn't seem to be working with my ink spell. Whoa. Hope I do better with the others. What I wanted to do tonight was not talk so much about chemistry, but talk about some chemicals have influenced our history. It's not an area that I usually visit, so I thought that would be kind of fun for me and a challenge. I think I'm going to skip real quickly through the slides that explain how the ink trick doesn't work. But I can say that here's what I was going to, whoops. Wanted to go back. I guess I need to do page up. I thought I'd talk a little bit tonight about nutmeg in New York. Doesn't sound like there's necessarily a connection there. I was going to talk about an enrichment blend. I was going to talk about snowflakes and a little bit about colors. So let's say I'll skip through the iodine clock reaction. Like I say, that hasn't worked at all. So I thought maybe it would be fun to look at some molecules. These are structures that are drawn in what's called the angle wire diagram. And each place that you see an intersection or a kink in the wire, that's a carbon atom. There are lots of hydrogen atoms that don't show up in these drawings. And everywhere that it isn't a carbon atom, we put down the letter for what kind of atom is there. It's a shorthand notation that lets us see structure. And so here's one molecule. Here's another one. Does it look very different? If you look in the upper right part, you just see a little double line flipping back and forth. And then here's a third one. And the structure just is like that long thing sticking out his neck, and the mouth opens up. See? Mouth is opening up like it's going to bite you. So what kind of molecules are these? Yum, yum, yum. They're tasty. They're spices like salt and pepper. And here's pictures of salt and pepper blown up, such as you don't normally see them. It turns out that spices were very influential in the age of discovery when it came to doing ocean voyages. Spices were so valuable that one of the first things that they used the ocean-going vessels for that had been developed with new technology was to go for spices. I'm going to tell a little story out of a book that's really fun. Chemistry books don't normally turn into bestsellers, but this is a great one. It's called Napoleon's Buttons, 17 Molecules That Changed History. And this is the first chapter in here, so I'm hoping to intrigue you into maybe reading a little bit more of how chemistry influenced history. So as I said, improvements in sailing ships and shipbuilding enabled longer sea voyages. The ships could stay out and brave the storms in the ocean better. And it turns out that spices used to come from the Spice Islands and the Orient through Baghdad, through Constantinople, which we now call Istanbul, into Venice. And Venice was really a rich state because it controlled all of the spices. In fact, if you wanted to buy a pound of cloves from the Venetians, it was 7 ounces of gold to buy a pound. On today's market, that means it's about $8,000 a pound for cloves. You can see why seagoing vessels might be interested in carrying something that was $7,000 or $8,000 a pound in our dollars. And the two countries that started off in this competition early on were Portugal and Spain. Here was the first thing they went for. This is the pepper plant. I just found these nice photos of these botanical specimens. And pepper came from over in the area of India. And people were interested in getting it because before the ages of refrigeration, they used it to help make meat that wasn't quite so good anymore taste better. And because salt was used a lot to preserve meats and foods, it helped make salty foods taste better too. Of course, the pepper is just a little berry from this plant that dries up. There's a little bit of microbial fermentation that goes on with it to give you the black pepper kernel. But both Portugal and Spain were interested in getting to the pepper. Well, they got to be so vigorous in their arguments about who had the right to which areas that eventually the Pope had to intercede. This was the molecule that was actually active in pepper. It's called piperine, and it's kind of a mild compound. You can see it's got a little bit of the same shape with some rings and a zigzaggy line coming off. But in 1493, it should sound like sort of a familiar year, Columbus was part of that movement, Pope Alexander VI issued a decree that said, you know, Portugal and Spain, you got to stop fighting over these places where you can get pepper. In fact, I'm going to draw a line, and Portugal can take advantage of all of the primitive lands to the east of that line to get spices or whatever, and Spain can get all of those to the west of that line. So interestingly enough, that was part of Columbus's motivation for going west. He said, I think the earth is round. A lot of other people thought it was that at the time. He said, I think we can go west and get to the same pepper country that Portugal can get by going east, and I think it might be faster, and the Pope has to let us develop that trade because we went west to get there. See, so he was kind of tricky. You can see that Portugal was kind of a bit slower coming in from the east. Remember Vasco da Gama? That was 1498, and Columbus has already come over to the west. Well, did he get to the Spice Islands? No. There were a couple of continents in his way that they didn't know about. I thought I'd show you a map. Here's the line that the Pope drew. You can see there's some chunks of land there. Well, Columbus didn't find piperine. He found a new kind of pepper. On his second trip to the New World, he found chili peppers, which was a spice previously unknown to Europeans. And the active ingredient in these was much hotter than piperine, so I mean, these had some real kick. Interestingly enough, he took them back, but they didn't catch on in European cuisine. But the people in the Middle East and the Southeast Asian parts just loved them and started cultivating them now. And as you know, if you want to go to a hot food restaurant, a Thai restaurant, they have some of the hottest food around. So Columbus was responsible for getting peppers to them. Here was a map of Columbus's second voyage. It was actually on Haiti that he first ran into the capsaicin-bearing chili pepper plants. Here's the molecule that makes capsaicin hot. It's usually in the lining of the seed cavity and the lining of the seed itself and the little stem connected to the seed. You can see again it's got a ring and a zigzaggy line, so that must be part of what plugs into our spice receptors in our tongue. Well, how about nutmeg? Turns out that nutmeg was a very rare spice. It only grows in a few isolated areas, really isolated. So it turns out that Portugal got an early step up on getting to the areas where nutmeg was produced, although the British started to come in too, and then later the Dutch. So you can see that in 1512, the Portuguese got there. We had Ferdinand Magellan from Spain come around, although he didn't quite make it to the Spice Islands. He got killed in the Philippines just before they got there. But in 1600, the Dutch started to take over. And boy, they went in very aggressively. They tried to get exclusive contracts with all of the chieftains on this little set of islands, which was the only place in the world that they could find nutmeg. Where was it? Out in the middle of the ocean. Here you can see a map that shows the tip of New Guinea, and the Philippines are just a little bit visible at the top. Where does nutmeg come from? A little group of islands right there. And we're going to talk about cloves. They came from another little group of islands right there. That was the only place in the world they were known of, so it looked to the Dutch like they could easily get a monopoly. Here's a map of the Banda Islands that shows them in more detail. You can see there's nothing else but sea around there. And they had exclusive contracts with all of the producers of nutmeg on all of the islands except the last one off on the left. That island is called Run. And it turns out that the chieftains didn't really understand the nature of an exclusive contract. And the chieftain there struck a deal with the British. And the British had a little bit of access to nutmeg there, which just drove the Dutch crazy. In fact, it drove them so crazy that they had 2 wars about it. They had epic sea battles. Here's a picture of one of the little islands. You can see a fresh volcanic flow coming down on the right there. Here was the nutmeg plant. This is the one that they were so interested in. Turns out that mace is another spice that comes from the same plant. If you look at the bottom center of the picture, that red stuff covering the outside of the gall, that's where the spice mace comes from. But we take the nut and grind it up for nutmeg. You're used to grating those, putting it on eggnog and so forth, but it was very, very valuable back then. So here was one of those molecules I showed you earlier that's called isoeugenol, and that's the active ingredient and essence of nutmeg. Here's a picture of the island that is close to where cloves were found. It's a couple little islands off the one that was at the top of that picture. Well, let me see what I should say. Can't see it very well here. You can actually see it about halfway up on the left. It says Ternate. That's where nutmeg comes from. So here's Ternate. You can see it's not a very big island. 2 islands like this, and it's about all the known extent of cloves was back then. Turns out that ginger also has a similar structure, although this one was much more widely distributed. And that's what that other compound was. And then here's ginger. That's the one that had the mouth open. So interesting that all these spices have a similar chemical shape. That's not unknown in biology, that there's a relationship between the shape of a molecule and its function. So structure-activity relationships are a big part of what biologists do with chemistry. As I said, a local chieftain on the island of Run had signed an agreement with the British, and it just niggled the Dutch to death. They finally said, okay, we'll let the British have Run, and maybe they'll get off of Manhattan, because they had sort of taken over Manhattan. And the treaty said, we'll let you have Run, give us Manhattan back. Neither side behaved very well, so they went to war a second time, and finally they came up with a new treaty that said, all right, why don't we just leave things as they are? we'll give you Manhattan, and since we've burned all of the nutmeg on your island, you don't need to come there anymore. So they ceded to Great Britain the island of Manhattan, which the Duke of York had illegally occupied since 1664, and that's when the British changed New Amsterdam to New York. So it was really these spice wars that were responsible for changing New Amsterdam to New York. I thought that was such an interesting piece of knowledge that I never had before I had read this book. That's when New Amsterdam became New York. So it was a chemical that did that. Spice monopolies eventually came to an end because they were able to smuggle seeds off and get them to germinate. Usually the Dutch treated the nutmeg seeds with slaked lime, calcium hydroxide, so that they could never germinate. But eventually some cloves and some nutmeg were smuggled off and gotten to grow in other places, and then the monopoly broke down. Eventually nutmeg was successfully grown on the island of Grenada in the Caribbean, and that's now known as the Nutmeg Island. So we get it much more locally now. Another book that I've taught from, which was about some interesting chemistry, is a book that's entitled Twinkie Deconstructed. This goes through all 39 ingredients that are found on the ingredients panel of a Twinkie, where they come from, how they're processed, why they use them, and whether they're good for us or not. And it turns out that I'm not afraid to eat a Twinkie because they're a lot better than I had thought. They have only one preservative in them, which is sorbic acid, which is found in the little Orange Mountain ash berries that the birds eat all winter in Montana. That's not really overkill with preservatives. What they've done is they put in a lot of ingredients that mimic dairy sorts of products which could spoil or turn rancid. Fats are replaced with things that won't go rancid so that it has more shelf life. And the shelf life of a Twinkie is only 3 weeks according to the bakers. But I opened one at the beginning of teaching this book in January and put it on a plate, and it's still sitting in my office, and it looks about the same. It's a tiny bit smaller and it's a little bit harder, but it hasn't gone away at all. So it's a very clever manipulation of ingredients. The chapter that I enjoyed most in this book is one that I find on lots of labels. You'll read the ingredients label and it'll say enriched wheat flour, and then it has a parenthesis, and it's got ferrous sulfate and niacin and thiamine, mononitrate, riboflavin, and folic acid. Just look at your ingredients panel, and that's there all the time. Well, I think this is kind of a neat story. Turns out that as our foods became more processed and we changed brown rice into white rice and whole wheat into white flour, we took away trace substances which all along had been helping us live correctly. So the more processed the foods were, the less good they were for us in the long run. So deficiency diseases began to emerge because diets no longer had these really important ingredients. One of them was pellagra. This caused 100,000 deaths in the southern U.S. because people's diets were mainly cornmeal, salt pork, and molasses. And you're missing niacin in that combination of foods. If you don't have enough niacin, you have severe dermatitis, diarrhea, dementia, and ultimately death. So, I mean, these are serious problems. Here's what the structure of niacin looks like. It's also known as nicotinic acid. They didn't want to use the name nicotinic acid, though, because it sounds like nicotine, and it's related to the molecule nicotine, and they thought people might have trouble ascribing health benefits to something that sounded like nicotine. So they changed nicotinic acid into niacin, but it's nicotinic acid nonetheless. Now these molecules are sometimes kind of complicated to make, and they were normally originally produced by extracting them from natural sources. Well, as chemists got better, we learned about more deficiency diseases, and we also learned how to make more complicated molecules in the lab. Some other deficiency problems that health officials had noticed was, of course, there was a lack of iron in many diets, causing anemia. There was lack of thiamine, which led to beriberi, which means I cannot, because people suffering from this disease have very stiff joints and can't move. Eventually they have paralysis that sets in. This was the difference between eating brown rice and white rice. There was lack of riboflavin in many diets. It caused mouth cracks, sores to open around the mouth and the nose, and your body to not be able to convert food into energy, which was kind of an important thing in biochemistry to have working. So the FDA said, you know what? Since chemical manufacturers can now make these substances more easily, why don't we just put them into the diets of everybody who isn't getting them? And they said, well, one of the most common food ingredients in so many different items is wheat flour. Why don't we just require the manufacturers of wheat flour to put these things in? And so in January 1942, they passed a directive that said this is going to happen. It was really a massive public health project, and maybe this is in the day before people got so engaged and angry about the government doing things, but I think it's really amazing that this got passed. It's not accidental that it happened during the war. Part of the campaign to sell it to the American public was that our troops were having problems from some of these deficiencies, and nothing was too good for our boys, so it helped sell the program that way. So nowadays, if you put wheat flour in anything, the manufacturers have already added these trace substances in there. It's kind of interesting where some of them come from. If you look at the ferrous sulfate, which is in there mostly for anemia, it starts out as sulfur in crude oil. When they refine the crude oil, the sulfur comes off and they can collect it as an element. They liquefy the sulfur from the gases and then burn it to make sulfur dioxide. This they pass over vanadium catalysts with water to turn it into sulfuric acid. We're eating sulfuric acid. I remember a little rhyme from when I was in Cub Scouts. Johnny was a chemist he's no more. What he took for H2O was H2SO4. And here we're looking at wheat enrichment, and we're drinking sulfuric acid. Well, they take the sulfuric acid, and what do they do with it? They put it in a big vat, and when they make steel plates, as the steel cools off, it gets this oxide coating on it, which is a problem as well as unsightly. So as they roll out these big sheets of iron, they take it through huge vats of this sulfuric acid, and over the course of the day, enough iron comes off of those iron sheets that crystals of iron sulfate drop to the bottom of these tanks. So they go to the steel processing plants, and they collect this residue, they purify it and grind it up, and that's where the iron in our enriched wheat flour comes from. So kind of an interesting story, right? Niacin, thiamine, and riboflavin are very difficult to prepare. Their chemical structures are very complicated. And so over the years, as a new trick has been discovered to make one of these vitamins, all of a sudden the discoverer has a huge market advantage. And in essence, it's been a series of single plants that have come up with breakthrough discoveries that have been the world producer of most of these substances. You can see these are complicated molecules. There's what the structure of thiamine looks like. It usually comes as a mononitrate. You can see a little plus sign there towards the upper right. It means we have to have a minus partner, and that's what the nitrate part is. Here's the structure of riboflavin. Although the bottom part looks like it's been run over by a car. It should be a zigzaggy line, but that's a special way to show the three-dimensional shape. So, These come mostly from single locations. Niacin is made in Visp, Switzerland, near the Matterhorn, from water, air, and liquid petroleum gas. So a lot of times they call it alpine oil now. So most of the niacin in the world comes from Visp, Switzerland. We stayed there and had pizza in Visp when I was in Europe in 2004 with my family. Thiamine is now made just north of Beijing from coal tar hydrogen peroxide, ammonium nitrate, and nitric acid, among other things. And riboflavin is still extracted from a natural source, but what they've got are some microorganisms that excrete it rather than having to extract it from plants. So it's done with a fermentation process where you feed certain chemicals to a microbe and it makes it as a byproduct. So those are where your vitamins come from. The FDA did add a new one to this list in 1993, and again, I don't remember any great hoopla about the public having a huge outcry about something being put into our food supply. What they found was that it reduced the incidence of neural tube defects in newborn babies by up to 70%. I mean, it was just a hugely significant study, so that they said, we need to put this in wheat flour to protect the population. They did this in 1993. The effective date wasn't until 1998, but the evidence was so overwhelming that the flour manufacturers started doing it right away. And when you look at the panels now, folic acid has been added to the list. It was originally found in something called Marmite, or also what's a Vegemite, which is a yucky yeast spread used by the Brits and the Aussies. We have an Australian citizen sitting here in the front row. Do you like Vegemite? No. My daughter Amy, who's here, brought a jar back no, it was Kinnerly. My older daughter brought a jar back, and I opened the lid and smelled it, and I said, ooh, I don't think I can try that. But anyway, folic acid was in that. It was later found in spinach leaves, so the name folic acid actually comes from the Latin folia for leaves. But it turns out that the artificially created folic acid is so much better than the natural stuff, or eating it in natural foods, because you can't tell what dose, and sometimes it depends on the conditions in which the plants were grown. So by manufacturing this substance and putting it in wheat flour, we're doing a good job of getting it to people in the amounts that are appropriate. So I just thought it was kind of interesting how that enriched wheat flour ingredient has come about. If you look at cookies that are imported from Scotland, like shortbread cookies, they don't have that enriched blend there. So maybe some of the other countries need to do that too. You can see how complicated folic acid is to make. Ooh. Okay, boy, I don't know, I'm a little hesitant to try another wizard trick here since my first one fell flat. I can't believe that. That's been a standard for decades. I've been doing that since 1977, and I've never had it fail. Always a first time. Well, I brought my freezing flasks, and this is a demonstration where I hope my spell works better. And here I am going to claim to use my magic powers to freeze right before your eyes a solution. And my spell goes something like this. It's in 3 languages, mostly in Latin because that was the historic language of Latin. Botanists and zoologists still are stuck with it in naming plants and animals. And healthcare providers talk about body parts in Latin. Of course, J.K. Rowling uses it in Harry Potter spells a lot. Some of it's in Spanish because my older daughter was a UM Spanish major and graduate from here. And I learned Spanish from her. If you can eat it, I can remember it. And the rest of it is in English. So the spell goes, medulla oblongata, et echinodermata, chiliana cheese enchilada, help gee whiz freeze this water. And then I snap my fingers and say, freeze. Is this going to do better? I'm really not doing well with my spells today. I say I am failing entirely. I know what the problem is. I usually lodge a couple of crystals underneath my fingernail, but I had a bicycle accident about 3 weeks ago, and I smashed my finger so hard that my fingernail fell off. So I don't have a fingernail for the particles to stick. But all I need to do is get one of these in, and then you can see it will freeze. Usually I snap my finger and it goes in. Like I say, I am totally failing tonight as a wizard. Whew. You're very kind. So I put this in here because what I'm going to talk about next is snowflakes, and they have some of the same process involved in their formation. So when I talk about my little freezing flask, I go into the chemistry of it, talking about things that are going to crystallize out, need to reach equilibrium and then start to crystallize out. And what we had is a supersaturated solution of a substance called sodium acetate. It should be a solid at room temperature, but it has such a complicated crystal structure that it can't get started. So a lot of times you have to have a nucleus for things to organize around. So what I did was I dissolved a lot of sodium acetate trihydrate. There's its formula in water on a hot plate. At a high temperature, it will dissolve easily. Then when you let it cool off, it supersaturates. Should turn back into a solid, but it needs a crystal because the 5-part formula for its crystal structure is complicated. How many times have you seen 5 cars crash together simultaneously and form a perfect star? That's what we're asking to happen to form these crystals, because these crystals are very geometrically demanding shapes. So unless it has a pattern to follow, it just sits there. Well, when I drop a seed crystal in with my little spell here, and you can see these are actual biology terms that I learned when I was getting my biology degree as an undergraduate. The seed crystal goes down and provides the template for the rest of the solution to assemble around. And if you look at it, the crystal emanates out from where that seed crystal landed in perfect rays. It also gives off some heat. In fact, this reaction is used in those little hand warmers that have a clicker, which nucleates the same thing, and then you can regenerate them by putting them in a hot pot of water. It's a nice recyclable demonstration. I can just heat it up and it will dissolve again. Here's a graph that shows how supersaturation and temperature are linked to different shapes of snowflakes. And I love being outside. I love being out in the winter, and I always wondered how snowflakes grew. And the nice thing about being in academia is if you find an area of a subject that interests you, if you're clever, you can turn it into your research. So what I did was I got an undergraduate student to decide that he wanted to do his senior project on snowflakes, and I was in business, right? I was just doing my job, and I got to study snowflakes. What you'll see from this chart is that as the temperature gets colder and colder, it gets colder going to the right. The snowflakes change shapes. There are certain temperature regimes and certain areas of supersaturation that lead to the nice dendritic ones that are the classical snowflakes. But there are some weird ones that are shaped like needles or columns or plates. And what I discovered is that there are some really strange ones. Here are a few little slides that show how the structure of water works into a hexagonal pattern. Water is H2O, so the little white spheres are hydrogen atoms, and the red ones are oxygens. Here you can see them stacked up into bigger arrays. And here you can see the hexagonal shape of a snowflake. And then down below you can see colored in red which set of atoms is making each of those parts of the hexagon. The basal face is the big face of the hexagon, and then we have the edges, which are called prismatic faces here. This material comes from some wonderful books on snowflakes that are shown here. I brought just one of them. This is a field guide to snowflake. Now, my wife likes to look at wildflowers and birds and all sorts of things like that. Well, I have my own field guide now, too. It's for snowflakes. Most snowflakes start out as tiny hexagonal plates. They probably start assembling around a grain of soot or a piece of pollen or a spore or a piece of grit blown in the wind. And the chemistry is such that if they have rough edges, there are more places for water molecules to stick, and so eventually we get this little faceted look. And if you look at a picture of a larger snowflake, you can usually see a hexagonal part way inside it. Snowflake development depends on what the humidity is, supersaturation, and what the temperature is. But when the conditions are kind of slow for growing, what happens is plates, hexagonal plates, tend to stack up. So we get thicker and thicker hexagons. So that's called end plate growth. If the humidity rises and the temperature is just right, then we get edge plate growth. And then the hexagon gets larger and larger across instead of thicker. And when the humidity is ideal for growing pretty snowflakes, what we get is the points of each of the hexagon starting to grow. If it's really fast growth, it's got rounded tips. If it slows down a little bit, it starts going back to its faceted shape. And once you have a faceted shape there, if you get the right fast growing conditions again, you've now got 3 points that can grow, and that's when snowflakes start to branch out. So you can get an idea of some of the things that happen to snowflakes. Let's see. Snowflakes travel through lots and lots of conditions between starting up in the air and getting down to the ground. They blow around a lot. The conditions are changing from high supersaturation to low, but the size of a snowflake is small enough that all 6 points of it are probably in the same conditions at any one point in time. So the same thing happens at all of the 6 different parts of the snowflake, which is why we get that wonderful symmetry. But there are so many different molecules that could hook on at any one point that there's no way that we'll get any 2 that travel through exactly the same set of conditions. So I don't think there's any chance of finding 2 snowflakes that are identical. If you look at the smallest possible visible snowflake, the number of water molecules in that is so large that if you did nothing all your life but count, you wouldn't even come close to counting how many water molecules there are. And since they can all line up in slightly different forms under slightly different conditions, we are going to have lots of unique little snowflakes. All of the snowflakes do preserve a 60-degree angle in all of their features. You can see that there are many parallel lines here that are related to one another at a 60-degree angle. And now what I like to do is look at pictures of snowflakes and look at their history. So you can see that this one was in conditions where plate growth happened for quite a while. The edges grew out, although there's a thick part in the middle, so we had some plate stacking, then we had some plate growth. And then right before it landed, it hit the fast point growing conditions, and those little facets at the end of an arm, all 3 sprouted out, and we had it happen a little bit on one of the arms. You can see that it's not totally symmetric there, but they're close. This is called a sectored plate. So we had some point growth, but then it slowed down, so each of the arms started to try to look like a hexagon again. You can see the hexagonal center part there. So like I say, most of them start out as hexagons. Here's one where the arms grew, and then it really got into the conditions for plate growth, and we have plates at the end of each of the arms. This one was on again, off again, on again, off again, with arm growth and plate growth. They get very elaborate. You can see that prismatic end like I was talking about, suddenly sprouting out and going in 3 directions all at once. So just a whole series of them. This one suddenly got good conditions for growing points after it had been, or branching, after it had just been doing straight rounded tip growing. Here we have some little collisions of the side arms. In fact, in our research, we used that sodium acetate to try to simulate collisions between arms on snowflakes. So I can actually show you a movie of Evan doing his thing. Let's see here. what we did was took the sodium acetate solution and poured it into a flat-bottomed Petri dish. We sent a camera underneath it, and then we made a little frame in the shape of a snowflake and put a seed crystal at the end of each of the arms and one right in the middle. So we had 6 points of nucleation. So here you can watch Evan make some crystals collide. Here's one where some of the side branches started growing like plates. This one has skinny connections in the middle, and they just got bigger and bigger as they came out. Really highly branched. So that's a classic dendritic snowflake. So just lots of really pretty shapes. Now, this is where the plate stacking got carried out to an extreme. These are rod-shaped crystals. It turns out that the edge, right around the edge, grows faster than the pit in the center, so eventually they develop a pit. And then if they run into a little bit more moisture, that pit can get sealed off. If they suddenly get into the plate growth conditions, then the column can be capped with a couple of hexagons. These are called capped columns. I remember running into these in Glacier Park on a ski trip. I was skiing along, cross-country skiing, and all of a sudden I looked down and I saw capped columns on my sleeve, and I stopped, and my wife skied into the back of me, and she says, "What's wrong?" And I said, "Look at your sleeve, capped columns, capped columns." It's just like when she says, "Oh, look it, there's a Swainson's thrush." Actually, she got appropriately excited. Now, there are people who have tried to come up with mathematical models that simulate how snowflakes grow. This is a wonderful site if you want to see some very elaborate models of how snowflakes grow. It's at the University of Wisconsin in the math department, and it will show you how a cellular automata actually, how a capped column actually grows, which is kind of fun. I went out on a number of early morning expeditions to look at frost. If you see the bushes like this, get really close. What you'll see is a whole bunch of one-armed snowflakes hanging on the branches. It's called hoarfrost. Here were some on the rosebud in front of our house. 60-degree angles throughout there, just like in the snowflakes. We grew some of these in the lab on fishing line. Fishing line happens to be a real good surface on which to start them. Here are some on a little piece of felt cloth out by our mailbox. You can see some nice stellar dendrites. My student Evan from Alabama said he was going to go up in the mountains to find some snowflakes. I thought he was going to be camping in the valley bottoms. He climbed Mount Brown in Glacier National Park and took this picture. I said, "Wow, that was so gorgeous, I couldn't have come down." He said, "Well, I didn't. I spent the night up there." "Oh, did you take a tent?" "No, I just put my sleeping bag down in the snow." And then a couple weeks later, he said, "Oh, I went out looking for snowflakes again." "What did you do?" "He climbed St. Mary Peak in the Mission Mountains and took this sunset colors." And I said, "Well, how did you get down? It looks like the day was almost over." "Oh, I didn't. I just stayed there and sat overnight." So I don't know about this guy from Alabama. He does things that I don't do. This was a nice little one that he caught on his mitten. We also tried to look at some snowflakes with the electron microscope. These are some images we found that people did with a special low temperature scanning electron microscope. It's amazing to see how precise some of the parts of the snowflake are, even at huge magnifications. So the bottom one is 36,000 magnification. We found some chunks like this. This was a Missoula snowflake that we caught on the electron microscope stage, we hit it with X-ray fluorescence, and it said, this is a little bit of sand. It was silicon and oxygen. There's some carbon there because there's carbon in imaging the screens. This was a little piece of soot. So these were what the original hexagon formed around when it grew a snowflake. You can see the carbon content of this one was higher than just the standard carbon background. So we wanted to see what some of these snowflakes were made of. Well, I know this demonstration will work. I just hope it doesn't work too well. Boy, like I say, I've had a bad night. So I thought I'd talk a little bit about color, and one of my favorite ways to get color is out of this bowl of alcohol. If we could have the lights down a little bit. I usually do this with a bit of Harry Potter flair too, and talk about the houses at Hogwarts. Of course, we have Ravenclaw, Hufflepuff, Slytherin, and Gryffindor, and they have banners that have colors associated with them. So we can light the bowl and say, if to Ravenclaw you're true, have this cauldron burn bright blue. We touch it with a match and we get a blue flame. If you aspire to Hufflepuff, fill this bowl with yellow stuff. We can get a yellow fire. Something new I'm going to try tonight. I don't know if that's a good idea, the way other things are going. If in Slytherin you're seen, have this cauldron burn bright green. That's a better green than I've been getting, so I think that one was a success. If in Gryffindor you'll bed, let me get rid of Slytherin here. If in Gryffindor you'll bed, have this cauldron show us red. So some nice colors. My grandpa used to have a can of sprinkles that he put in the fireplace, and now I know what he was doing. We can get some slightly different effects by putting a couple of other substances in. My wizardly might can shape and mold this cauldron into sparks of gold. Show these muggles a wizard's might. Fill this bowl with sparks of white. That one worked. Thank goodness. So what we just saw was some manifestation of the electronic structure of atoms. This is what really got scientists excited about this back around 1860, when certain elements were strongly heated in an electric arc or a flame, and the color was put through a prism. It turned out that rather than having a complete spectrum of colors like the rainbow, it was bright lines. And what happened was that they were seeing the first evidence that electrons around atoms only come with certain energies, and each energy has a different color. Here are some of those bright line patterns that they found. You can see the elements that gave rise to them on the right-hand side of the screen. You can see three of them that I used tonight. Sodium was the yellow color that we saw, copper was the green, and lithium was the fuchsia. Sometimes I do potassium, which is a nice lavender look to our eyes. Well, these bright lines landed at different wavelengths, and mathematicians came up with an equation that would predict where the next line was going to be, which says, this must really be significant. So the race was on to understand how all this fit together. I get terribly excited with this demonstration when I have kids in front of me. So here are the things I just put into the fire for you. These are slightly different than what they use in commercial fireworks, because those burn at a different temperature up in the air. They use barium to get green in aerial fireworks, and they use copper to get blues. And they use strontium to get red. The electrons are restricted to certain regions of space, depending on how much energy they have, and only certain energy values are allowed. So it's not like having a ramp to go up, it's like having a staircase. So there are only certain levels that you can stop at. So here are a couple of shelves to hold electrons in an atom. This one is meant to show lithium, which was the magenta color. It has 3 electrons. When it goes into the flame excites the outermost electron on the highest shelf, and it leaves or goes to a higher level. There's a vacancy. When it cools off, it doesn't like a vacancy there, so it grabs an electron from anything that it can, and as that electron drops in, it gives off a color that's equal to the energy of the drop that it just made. And since there are a whole bunch of shelves in these atoms, we see a whole bunch of different lines. Here's the colored lines for lithium. We can see some sharp lines at these nanometers, these wavelengths. Here's a principal line at 671, a diffuse line at 610. Anything interesting about the spectral categories? This is for my chemistry students. The next category is fundamental. What you'll see is the first letters here of these different categories is how we eventually came to label the shelves of these different energy levels, S, P, D, and F. Here's a picture of some of the energy levels that are available, and you can see that S, P, D, and F. So it came out of these bright line spectra. While we're talking about colors of sparks, we're looking really at temperatures. So some of this was flame emissions, that was electrons being excited. Some of it was sparks, and that was just little pieces of solid that were burning and making an oxide, and depending on its temperature, it was either cooler and looked orange, or hotter and looked bluish white. Turns out that the way our eye works, there's some debate on this, but humans are generally considered to have what's called a trichromic color vision. That is, we have 3 different kinds of color receptors in our eye. A lot of times they're called red, green, and blue receptors, or long, medium, and shortwave detectors, although I found in doing some research that up to I think that's supposed to be 10% of women have a genetic variant that sometimes gives them a 4th color receptor. So maybe that's why they're so conscious of style color sometimes, is because they have an enhanced ability to detect different kinds of colors. Even with our 3, we can usually distinguish more than 1 million different colors with our eye, which is amazing. Here's the sensitivity of the different photoreceptors at different wavelengths. That's how we measure what the energy and the type of radiation is. And you can see the shortwave one is the blue, the mid-range one is the green, and the long one is the red. I made this little diagram because this is the way colored light works in the theater. And actually, if you look at the secondary colors there, this is the combination of colors they use to print colored pictures in the magazine or newspaper. The primary colors are red, green, and blue, which is just stimulating one of the kinds of receptors. If you hit red and green equally, your brain sees that as yellow. So when you see yellow light, you don't know if it's yellow light or if it's red and green at equal intensity. When red and blue are mixed, you get magenta, and when green and blue are mixed, you get cyan. You'll notice those secondary colors are very common colors you see on the computer screen. On the computer screen, there are only red dots, green dots, and blue dots, and they're just lit up in different combinations. I tried to show that by drawing some lines on the screen. I don't know how well this will work. You see 2 yellow lines, 2 purple lines, 2 cyan lines, I should say magenta, 2 cyan, and 2 white lines. If you scale them up, you can see the top one is really a green line and a red line drawn very close together. The third one down is a blue line and a red line very close together. That's the magenta. The next one, color combination, you can see the blue and the green, which is supposedly makes the cyan, and the bottom one is actually 3 different colors. Now I'll back up again. And if they squirt kind of close together, your brain blends the colors, even though it's red and green in the top one and yellow on the screen in the bottom one. But they're being made the same way. But I just thought it might be interesting to try that. So we have the rainbow. This is a rainbow in Alaska that I found at Wikipedia. And I've always been curious about the colors of the rainbow as I was taught. Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. I was kind of suspicious about that indigo character. Turns out that if you historically look at what Newton reported, he just reported 5 colors. And then later on, he wanted to ascribe some significance to music of the spheres. There were 7 heavenly bodies that were observed, 7 notes to the scale. I better have 7 colors in my spectrum, so he added indigo in there. Chemically, the dye indigo is the blue that they use to make blue jeans. So here's that makeup of 7 different colors. Now, I had trouble figuring out how to do this. I think really Newton meant the 7 colors if he wanted 7 to be red, orange, yellow, green, cyan, blue, and violet. I think that's what he should have done. Of course, it doesn't make a nice little acronym like Roy G. Biv. So I don't go along with Roy G. Biv. So I think the colors of the rainbow really are more red, green, blue, yellow, cyan, and magenta. So with that, I'm going to let you ask some questions and have to apologize for my ineptness as a wizard tonight. Man, I can't believe that I didn't get my ink to work. Whew. I'll have to figure out what in the heck I did wrong. I can answer questions right from here. Absolutely. The chemistry of petroleum is not very extensive, but it does do one thing very well, which is burn. And after we've burned it, it's gone. It is the chemical feedstock for so many things that we depend on that I think we need to start not burning it in many instances. We need to come up with other alternatives. I think heating buildings with fossil fuels is not necessary at all. With architectural designs that are now available, we could do a lot of space heating with passive solar and active solar that would completely negate using some of the petroleum products there. I also think it's terrible that our motor vehicle fleet averages for mileage are so low. I've got an ad from the 1930s that says all this in 24 miles a gallon, and that's currently better than our fleet average. Of course, they didn't have the emission controls back then to have to power through, but I think it's deplorable that we have vehicles that don't get better mileage. And we're running through our petroleum, which is getting harder and harder to get. They keep finding new ways to get more out and finding more supplies, but that's not going to go on forever. And certainly the location of the fossil fuels leads to political situations and conflict, just like the spices did in the old days. I don't think we would have conflict in the Middle East if that's where the world's supply of cauliflower was. Any other questions? Back there I see.
Are there things about the chemical structure of spices that makes them more pleasant to our sense of smell or taste than just other chemicals, say like alcohols or oil? Or what is it about the structure of those spices chemically?
So I think the spices have that structure-activity relationship that I was talking about, that they land in receptor sites that trigger certain kinds of responses. Really hot things like the capsaicin actually release endorphins, which are feel-good chemicals to help dull the pain, and part of the satisfaction of having really spicy food that way is from the endorphins that are released. Some of the others, I think, just trigger what we consider pleasant responses. I could bring a bottle of benzaldehyde into the room, and people say, ooh, benzaldehyde, that doesn't sound good, and I take the cap off. Almond, that's what the essence of almond is. So there are different categories of organic compounds that that will elicit pleasant responses and others that elicit bad responses. But definitely there is that relationship, and they use that same structure relationship in looking at trying to design effective medications and also in designing pesticides or antibiotics. So that molecular shape is definitely in there. The spice molecules typically are a category of compounds called terpenes, which are built up by plants. Most of them are probably there as natural insecticides. Since plants can't run away like animals can or swat things, they developed these things like capsaicin to make it unpleasant for herbivores to chew on them. And they use isoprene to assemble these terpene molecules. Turpentine is full of them, and actually it has a nice piney fragrance. So I think that the molecules that are built from the terpene pattern are more pleasant to us. Some things are not pleasant to us. Butyric acid is one of the main odor ingredients in vomit. So if you look at the label on that bottle, it says caution, stench. So that receptor leads to a very unpleasant result. And then there are other things like putrescine and cadaverine. So nitrogen compounds tend to have bad smells. And maybe that's so that we didn't eat them because it was a sign that the meat had gone bad. And we needed cloves and nutmegs to disguise it.
One of the holy grail chemistry questions in Montana right now is how to break the cellular bonds of wood fiber and turn them into fuel. How come it's so hard to break those bonds in an efficient way so that you don't have to use more energy to break them than the fuel energy you get out of them, so you can make biofuel?
That's it's a good question. Certainly we don't have the enzymes that break the bonds in wood molecules. They have cellulose fibers in them. Some animals have microorganisms in their guts that can do that. But there must be something about that linkage that's particularly difficult. Not my particular area of specialty, so I'm not quite sure how that's going to happen. I was familiar with a person in Bozeman that was working on some microorganisms as a culture that could try to break down the cellulose in seed hulls so that they could turn it into biodiesel, trying to make that happen. There certainly is a lot of biomass out there, and if we could figure out how to do that, it would free us up to use the petroleum products for better things. Anything else?
If there are no other questions, then perhaps I can invite you all to stay. We're going to have a reception. Please hang around and get a chance to talk to Garon.
I do have 2 more flasks we can trip. I brought 4. One of them tripped just from the vibrations on the way over. It was a challenging night as a wizard. Woo. But thank you so much.